Well, Marty, I think we're at 3:02, so I think we can get started. I know there's probably some more people wanting to jump on, but we can at least, get things rolling here.
Sounds good.
So I'll go ahead and start with this particular working group. All our working groups over the last, say, year and a half, we have been trying to make them a little more technical, a little more detailed, and have ample time for questions and discussion on basically the river and its processes and how we're addressing things. So that's the aim of these, is to just get a little more technical, a little more in depth, and allow a lot more questions and answers and things like that. Today, what we're going to do is we're going to talk about the features and strategies that we're using for the Meadows project, and also what we did before with the restoration projects, because they actually feed in to the Meadows project. I mean, a lot of the things that we learned from the downstream restoration projects when we worked as a team member, we're going to be applying a lot of these things at some of our sub projects, such as Vista Narrows and the Rock McCarran Reach, and perhaps even the airport reach. So there's a lot of things that we've learned, and we wanted to share those with you and also get some feedback and questions and discussion on it as well. So the first talk is to talk about a little bit of the past with the restoration strategies that were done in the past, and Danielle will be handling that. And I think I will just kind of shut up and let Danielle talk. As you know, many of you know, Danielle has been with our organization for over 15 years, and she was involved and was a part of many of these restoration projects. And she has spent considerable time monitoring these projects and looking and assessing how they worked. And she's also been very involved with the Vista Narrows on the environmental aspects, the permitting, the vegetation, and how all that's working. So she's really well equipped to give this talk on what happened with the downstream restoration and our part of it and how that will apply going forward. So with that, Danielle, I'll let you have it.
Okay. Wow. Well, thanks, George, for the lovely introduction. I really appreciate it, especially because I just realized that I did not include a title slide with my talk. So I'll be sure to add that. But I'm Danielle Henderson. I'm pleased to be here presenting sort of a summary of features and strategies and the outcomes from the downstream restoration projects that we have participated in and implemented as part of the flood project. So I guess I'll just jump right into it. Many of you are probably familiar with this, but I just wanted to refresh and give you kind of an overview. What is a floodplain? It's basically the bottomlands area adjacent to a stream channel, and it floods from time to time. And as part of that and the river dynamics process, you end up with all of these features that are associated with a meandering stream. We've got meander scars, we've got oxbow lakes, there's areas of deposition and erosion, and there's backwatering areas, and then even some natural levees. So that's just kind of a really quick overview on floodplains. And let's see, I'm not sure why it's doing this. Here we go. Okay, so what are some of the benefits of natural floodplains? There are many. I'm going to highlight some of the benefits that are really important to the flood project, and those are related to hydrologic function. Floodplains allow for storage of floodwaters and also conveyance of floodwaters. It's space for the water to spread out and also to infiltrate into the ground. It can reduce flood velocities and flood peaks because, again, you can slow that water down, spread it out over the floodplain area, and also have it absorb into the ground rather than continuing on downstream, contributing to the peak. And it can also reduce sedimentation because of, again, slowing down the water, the sediment drops out. And so that is also a water quality benefit. Natural floodplains also allow for groundwater recharge, which is important for the plants along the river in wetlands and whatnot, and also for the wildlife there. And I'm not sure why it's not letting me do that. Anyway, okay, to continue with some of these benefits, again, like in terms of biological productivity, they support high productivity, they enhance biodiversity, complex habitats on the floodplains allow for a variety of wildlife species to live there and survive. They preserve wetland functionality. Again, a lot of that is due to higher groundwater tables and sustaining the plants that are part of the wetlands. They maintain ecosystem integrity. They offer breeding areas and rearing areas for various wildlife species, including, if we're talking about the in-channel, the aquatic areas, and then, of course, the areas in the floodplain right next to the river for various fish and wildlife species. And those species, because they have that habitat, they are, they can be protected and they can actually thrive in those areas. So they're really important. Here we go. Right. Okay, and I'm sure many of you are familiar with these statistics. Again, this is just kind of an overview of our particular watershed and why floodplains are so important, the river corridor, and just the importance of those river corridors in Nevada in particular. We are very, very arid here, and rivers and riparian areas, the floodplains, support more than 90% of our state's biodiversity. The Truckee River is home to 2 federally listed fish species, including the Lahontan cutthroat trout and the kuiwi. Lake Tahoe is the headwaters of our watershed. It's, considered a national treasure, and we have a closed basin. So we've got Pyramid Lake at the end of the Truckee River system, and among other things, it's sacred to the Pyramid Lake Paiute tribe. So it's a very important system. It's highly regulated, and the river also provides more than 80% of our community's drinking water. So we have a lot of reasons to try to preserve the floodplains that we have and restore floodplains when we have an opportunity. Oops. Okay, so what happens when natural floodplains are impacted? Well, we tend to develop in a lot of floodplains because they're flat, and in the beginning they had fertile soil that was used for agriculture, and those have been converted to industrial, municipal, commercial use, homeowner, building of housing developments and whatnot. And so, when you impact those natural floodplains, you take away that storage. And so I'm not even talking about the sort of ecological impacts, but you're taking away the flood storage capacity. You are creating a lot of impervious surfaces, so the water is not infiltrating into the soil. And you've constructed a whole lot of expensive buildings and structures in the floodplain. So now all of those need to be protected. And so, as you can see here, our area has a history of floods. This is the 1997 flood. And, the water's got to go somewhere, and the river doesn't really recognize whether it's a developed floodplain or a natural floodplain. It will flow where it needs to. And so what ends up happening is you sustain a lot of damages through those types of floods. And again, so I mentioned, there's a variety of reasons to to preserve natural floodplains when you have a chance. And you can do that by conservation easements, purchasing pieces of floodplain property, and and avoiding development in those areas. You can also restore the floodplain where you have opportunities. And again, it's about being able to restore the land and manage the land afterward. Some of the reasons to do this would be, as I've talked about, flood attenuation. Again, you can restore the channel sinuosity, put the curves back in the river, and reconnect that river to its floodplain so that the water can infiltrate, it can spread out, it can contribute to shallow groundwater throughout the seasons and sustain plants. That's definitely our top goal, I would say, in terms of why the Flood Project is interested in floodplain restoration. Also, we're very interested in creating and enhancing habitat for aquatic, riparian, and wetland species. We have, again, the federally listed fish species, as well as a lot of migratory birds and other endemic species that are really important for our area and for Nevada. Water quality, as I mentioned, a large portion of our drinking water comes from the Truckee River. And so if we can reduce sediment loading and increase the capacity for nutrient uptake and also reduce the temperature of the river by shading from vegetation along the banks, that will definitely improve water quality over time. And we're also interested in managing weeds. We'd like to control and reduce the spread of invasive and non-native plants and make sure that the native species have the ability to compete and thrive in these areas. And this gets back to, there's a few people in the audience, I think, who are actually members of our old community coalition. And, the vision for the Flood Project, like George says, I've been here for a while, not since the very beginning, but certainly since I've been here and before that, the vision was always to create a healthy, functional river system while providing these flood risk reduction benefits, right? And so the way we plan to do this is to have a combination of setback levees, flood walls, terracing, bridge replacements, floodplain land acquisitions, restoration, and also some urban parkways. And I know George's presentation will get into more detail on some of those features, but it was always, it has been and continues to be that sort of vision for a functional river system that is also managed to reduce flood risk for the Truckee Meadows. And stakeholder engagement is key over time. Again, we've engaged with our stakeholders. The Community Coalition is now the working group. We also have our Technical Advisory Committee. We've got partnerships with all sorts of entities. We do education and outreach. And we've established ourselves over these years and also in recent years under, I would say, George's leadership as a resource for the community due to our technical expertise, some of the tools that we can offer, and also the support that we give to emergency managers during flood events. So along those lines, working with a lot of other partners, agencies, nonprofits, we have implemented a restoration program in the lower river as part of the flood project. And in total, we've invested about $6.9 million to help restore the lower Truckee River. And again, like I've mentioned, the benefits of this from our perspective include flood attenuation, the decreased risk of developed property damage by preserving and restoring these floodplains where we can, stream bank stability. So the stream is the system is more resilient and it won't unravel during some of these larger floods. And along with that goes sediment retention, which again leads to water quality improvement. So over the course of this program, we have helped restore about 8 miles of the river and helped to create over 450 acres of habitat in and along the river. So it's been quite a large effort. again, I just want to mention, we have a lot of partners in this effort. And one of our major partners who actually was responsible for, implementing a lot of these projects. And then, we and some of these other entities help to fund and manage parts of the projects. The Nature Conservancy was basically the lead on a lot of these projects. And so I just want to acknowledge that and again, mention how much we appreciate all the efforts that they have undertaken on the lower river. This is just an overview map of the lower Truckee River reach. This is from, it's a fairly old map, but it's easy to identify all of these restoration sites. And again, this is going upstream to downstream. These sites were identified and sort of assessed as far as existing condition and then for the potential for restoration, and also like the level of restoration that could be undertaken on each of those sites, a low level versus a high level. Low level might be sort of almost passive restoration or just smaller measures like maybe excavating some floodplains and seeding with vegetation versus something like full channel restoration where you're realigning the entire river channel in that reach and doing major earthwork and earthwork in the channel as well to create in-stream habitat. So sort of different levels of proposed restoration. And this was done in 2003, I believe, and that was by Otis Bay, working for the Corps of Engineers. So these sites were later sort of incorporated into flood project plans when we were working on the core project, and also in plans for Question 1 funds, which was a program, a bonding program that was undertaken by a whole consortium of folks to restore the Truckee River and acquire land to preserve it and also to add recreational features. So these projects were incorporated in several different like major planning efforts along the river. And of those, we've been involved with a series of those projects. Again, as part of the flood project, working with the Nature Conservancy and other folks. So I just wanted to kind of give you a summary of those, going again from upstream to downstream. The Lockwood Restoration Project. And so what you see here is Google Map view, the most recent ones that I could pull off the web. So it shows the sort of condition of the projects today after construction. This particular project was constructed in 2009, and then each of these projects has a vegetation establishment period afterward. That's after like the major earthwork is done and in-channel work is done. And that's usually about 2 years. And then after that, it kind of goes to a monitoring and maintenance phase. This particular this particular project rather, restored about 0.6 miles of the river channel and also created about 36 acres of wetland and riparian habitat. And you can see some of the features here. I don't know if you can see my mouse, but there was a meander bend here that was excavated, and then there were floodplain areas that were excavated and planted with native vegetation. Some in-stream riffles were added, and there's, so you're adding a various riffle and pool segments in the river, and those serve as habitat for fish and also the insects and other creatures that the fish feed on. It creates channel complexity, and so when there are periods of low water and higher temperatures, the fish have areas to hide temperature refugia. They're cooler areas, deeper water. And so they can get through those stressful times in the river. And there are some meander bend sort of cutoff areas here where these can provide backwater habitat for various species. And again, the pools and riffles. So, even though this project was a little bit smaller, it still had a sizable impact on the river. And one of the other things that was done as part of this project was the creation of a recreational trailhead. So, so again, it's open to the public, and it's managed by Washoe County as a park and trailhead. And so, the public is able to come and access the river and enjoy this area as well. So that's another important piece of these projects. The Mustang Ranch project is just downstream of Lockwood. Construction again completed in 2009, followed by a vegetation establishment phase. And here you can see a lot more work. This was a high level of restoration. So a lot more work was done to realign the channel and create sinuosity in the channel to slow down the water, to allow the water to flood its floodplain. There were lots of wetland and riparian plants that were included in the revegetation plan, cottonwoods, willows, other wetland plant species. And this was all done also in concert with weed treatments. So, those species were able to establish over time. You can see, there is a green belt here along the river. And this also has, again, these backwater areas. This particular project restored about 2.5 miles of the river channel and created around 186 acres of habitat. So this was a much larger project than Lockwood. And there's fishing access at Mustang as well. So downstream from Mustang is the McCarran Ranch Preserve. This property is owned and managed by the Nature Conservancy. And I think it's important to look at this particular project because this was the first major project undertaken by the Nature Conservancy on the lower Truckee River. And it was really important because it served as a blueprint for restoration in this area of the river. And they developed all sorts of methods for sort of ensuring the success of these projects, because it is kind of a challenging environment to try to restore and also revegetate based on, the weed issues that we have and also the climate. And they also prepared something that came out of this effort was sort of a manual for how to permit these projects too. Because at the time that this was done, it was, I don't want to say it was new to the regulatory agencies, but just navigating the permitting process in this area and in our watershed was a bit tricky because of, again, the fact that the river is so highly regulated. And so the Nature Conservancy, by doing this work, they established themselves as an entity that could deliver on these projects and implement these projects successfully after being able to obtain these permits. And so that information was passed on to all sorts of other agencies in the area who wanted to do restoration work, and it's been really helpful for the subsequent restoration projects. And the McCarran Ranch Preserve is also open to the public. You can see here in terms of features, a lot of channel work was done. This particular property is wide, so there was a lot of opportunity to come in and do floodplain terracing, excavation, and revegetation. And there's a very, I would say, healthy cottonwood canopy and understory out here. There's a trailhead, and there are some trail maps online. You can come here and do wildlife viewing along the trail, and it's open to the public. So it's a really great place to visit as well. We also partnered with the Nature Conservancy and others to do some work at the Tracy Power Plant. So even though it's a power plant and there's an industrial uses going on, we did preserve this pond at the request of NV Energy, who uses it as part of the operations here. But there was work done here in terms of channel excavation, floodplain terracing, revegetation, again, kind of the same recipe following the other projects. This project was completed in 2013, followed by that vegetation establishment period, restored about 2.5 miles of the channel, and created over 114 acres of habitat. And this is the final project that we've been involved with. This is the 102 Ranch Restoration Project. And again, this is a large piece of land. And it is so similar in scale to the Mustang Ranch. And again, lots of channel work was done here. You can see these meanders that were excavated. There's some cutoff sections here and a little bit of a pond that floods when we have higher flows. But again, it's spreading out that water into these riparian areas here. And you can see all of the cottonwoods, willows, other wetland plants that are in this area. I encourage you all to drive I-80 and stop at some of these trailheads. It's pretty impressive if you go and look at all of the vegetation that has established itself over all these years. There's a trailhead here as well, so you can visit that area. So again, just to sort of recap, I mean, what we're hoping to do with floodplain restoration is also, restore and enhance the ecosystem. And here we've got a variety of species shown, including the Lahontan cutthroat trout. I think that's a leopard frog. We've got mule deer. There's lots of wildlife species and aquatic species that benefit from these projects. And over the years, we have implemented an in-house monitoring program. We've monitored shallow groundwater through a network of piezometers. We've taken water quality samples, just grab samples in the river. We've also collected meteorological data, weather data, such as, wind speed, velocity, precipitation, etc. We've conducted vegetation surveys to see how the vegetation has established over time and, percent cover versus bare ground, and also different types of species that have established. We've done geomorphic cross sections, and a long time ago, we did at least one round of benthic macro invertebrate sampling. There's also a wide variety of data that has been and is being collected by others, including the Nature Conservancy, the Audubon Society, NDOW, Fish and Wildlife Service. There are wildlife surveys, bird counts that are completed. There's fish that are collected in the river. There's water quality, that is water quality sampling conducted by the state and DRI and others. USGS has a network of stream gauges, and we also participate on the operation and maintenance of some of those through our flood warning system gauge network. So there's a lot of other data that's being collected in this area as well. We had our consultants, Dyer, now JUB, conducted a study of downstream impacts that was related to some of the work we've been doing with the Pyramid Lake Paiute tribe. And one of the things they looked at were these restoration sites in terms of how the river functions in these restoration sites versus, if they, well, how it functions and what they found. And I'm sorry, I meant to include a graphic of this in the presentation, but what they found was that those restoration sites do attenuate floodwaters. And George can probably speak to this, but I believe it was even up to the 50-year flood, there were significant impacts or benefits to having those restoration sites in place and preserving those natural floodplains. And I guess as part of this talk sort of kicks off an effort for me to sit down and sort of compile and start going through a lot of the data that we've been collecting. We have a lot of data. What I need to do is sit down and create a report that summarizes the data and sort of shows the success of these projects in terms of, the metrics of all these things that we've been collecting. And from there, we can sort of decide what the next phase of this monitoring program might be. Do we continue monitoring the same things that we have been? Do we expand? Do we have new questions that we'd like to answer? And are there things that need to be done on these sites for the future in order to make sure that they continue to function as designed? The Nature Conservancy has been very diligent in doing a lot of maintenance on these sites, but they're sustaining, self-sustaining, you could say, but there's still treatment, weed treatments and cleanup after some flood events that needs to happen. Perhaps some replanting of vegetation over time, that sort of thing. So that's kind of just a sneak peek of the future. And so in summary, I would say, we're still very committed to the original vision of the Community Coalition. And again, our goal is to design and construct a project that not only reduces flood risk, but also provides these ecosystem benefits and even some recreational access opportunities. And again, the overarching goal is to create a more resilient community. And that's, the human community and as well as the wildlife community and plant community. To accomplish this, we are using the best available technical tools that we have today, which of course are much improved from the tools that we had in 2003, 2010. We have some innovative methods to achieve this goal. And these restoration projects that were completed earlier serve as a really valuable reference for other portions of the flood project. And George is going to speak to this in his presentation. We're using these restoration projects to inform the design for Vista Narrows and also for the Rock McCarran Reach. So with that, I am happy to answer any questions that you might have. And I will stop sharing my screen too.
Any questions?
Everybody's waiting for George's presentation.
Yeah, watch that participant thing. It'll go way down as soon as I start talking.
Oh, all right. Well, thank you so much for your time. And we've got more time at the end for questions if you guys think of some things. But with that, I'll turn it over to George.
All right. Yeah, and that's a nice setup for what I want to talk about. And I do want to talk about a few things that have changed over the years and how we're going to use these newer tools and information gained in what we do forward. So I'm going to go ahead and get the screen shared, and there should see title slide up. And we'll go ahead and get started. So I imagine there's a title slide up. Is that correct? Can somebody confirm?
Yes.
Yeah. Okay. All right. So basically, we're going to talk about features and strategies proposed for Vista Narrows and the Greater Meadows Flood Project, which the Greater Meadows Flood Project, when I say that, is really the project from the freeway bridge on 395 all the way down to Vista Narrows. So it's that reach of stream that has some of the greatest impacts because it's so flat there and the water can really get into these big, wide floodplain areas. So what I mean by some features and strategies, first of all, and it's kind of an underrated thing that I think a lot of us just are growing, or, we're used to it and we're kind of like a frog in a boiling pot. But um, first of all, there's the extensive use of 2D modeling to test and game configurations and treatments under various flow scenarios. So in the past, as I'll show in a slide here in a minute, I mean, this is new stuff. I mean, honestly, 2D models were not widely used until after the year 2000, and those early implementations were limited. And you can see around when, for instance, when HEC-RAS came out in around 2014, 2015, there was a greater a greater use of these models, including HEC-RAS, which is one model, the 2D portion of it, and then also other models. I remember starting in my career, starting to really use these models quite a bit in the late 2000s, like 2007, 8, 9, 10. That's when I really started using these models. And honestly, I didn't see it very widespread before that. I saw some things with something very expensive and very focused. So that's one thing. The other thing is in this particular, project that we're doing, we're using strategically use of low terracing. We're not just throwing out low terraces. We're learning from what we did downstream, and we're also learning from these 2D models exactly what kind of impacts a terrace can have. For instance, if you widen out the channel, you lower the velocities in overall, typically, you can lower the water levels. And depending on what kind of vegetation you use and what kind of treatments you have on the ground, you can mess with the what's called the roughness and change water levels and velocity. So all those things you can start checking with a model now. In the past, we just kind of guessed at it. And I mean, yeah, I'm an old guy now, and I was kind of artsy, and I do things like look for, prototype reaches and then just imitate the reach and things like that. Now, I mean, I can start to really look at the impacts of things because there's finally enough detail in the model, in these models that are being developed. And these models are also calibrated and perhaps even validated. So they're a lot more accurate than they used to be. And the terrain is a lot more accurate because of the onboarding of LiDAR. There's a lot more LiDAR data out there. There's a lot more detailed information out there. The other thing is the use of channel configuration and roughness to manage velocities, which I kind of alluded to already. And then also, this is a specific thing that I'm thinking about, or, we'll have to have this vetted through a design process, but the use of a recreational wettable area to provide strategic storage to attenuate peak flows at critical times and stages of flood flow. So yeah, there's been wettable areas, there's been detention basins forever, but getting that detention basin to be optimal to to only come online at a critical time during a critical part of a peak flow, you have to kind of have an idea of what the hydrograph might look like. And you also have to have an idea of what the water levels are and everything else. And that feeds right back into number one with the modeling. Without the model, I can't really optimize that. There's no way to really do that. And if it's not detailed enough or not accurate enough, it's just not going to be very helpful. In recent times, we're getting that kind of accuracy where we can start to game these things, do trial and error and things like that, and find the optimums. So two-dimensional modeling, the design process. This is just a little slide, and we're going to have all our slides up. We'll put them up as PDFs on our website. This is also being recorded as a audio, so you can follow along if somebody wants to do it later, or you tell somebody, hey, George really blew it on slide 8. You should hear it. He just lost it. So if you have something like that, you can, come back to it and do that sort of thing. But basically, this idea of modeling is very new. It's not something that we've been doing for a very long time. The HEC 2 model was developed at first in 1964. That's when I was a little kid, but you may say, well, that was pretty long ago. But that was on a mainframe computer, and the only way that you really input it into it was through a card deck. And I actually, in my early career, I actually did some of that in college. And I can tell you right now, I had, when I saw that stuff in Florida during the election in 2000, I was having nightmares about my experience trying to input into a computer, all these things through a card deck. It's very, tedious to say the least. Now, a big thing was in 1981, with the advent of the PC and the Apple II and all that, HEC 2 was ported into DOS, and that led to widespread use in floodplain modeling. In fact, the current Reno floodplain, I know there's been updates with what's called LOMARs, letters of map revision, but the base map is actually from 1984. So it was one of those first generation things that was done after the advent of the PC, and it was done in HEC 2. Also in the 1970s, maybe even a little bit earlier, the first 2D models were developed on mainframes, and one of them is RMA2. That's actually one I'm ashamed to say that I have worked on, and they were written in the Fortran computer language. They're very unwieldy, very unstable, very hard to work with, very hard to input. But they were 2D models. In 1987, the conceptual basis of Flow 2D came out, and that was the first application of it was a mud flow model, and that was by a person named O'Brien. And Flow 2D for a while was a very heavily used model. HEC-RAS, which is an extension for or a fork of HEC 2, and it's really reworked, okay? So I'm not trying to minimize the effort that went on there, but it had the same kind of goals and aspirations as HEC-RAS, as HEC 2. It was first developed in 1995, and it became quickly a standard model. I mean, everybody was using one-dimensional HEC-RAS at that point. A lot of people were using it. And there were other modeling things that were coming up about that time. There was a Dutch Institute, and they had something called Mike. And they had first a 1D, then a 2D model as well. There were other 2D models. Some common ones that were used a lot were Flow 2D, which I actually used quite a bit in my consulting when I worked for a consultant. 2Flow, I've used once or twice. River Flow 2D was actually kind of my go-to modeling for design until HEC-RAS got halfway decent. And then there's SRH2D, which is a Bureau of Reclamation two-dimensional model that I've also kind of ran across a few times. So these things started to become more widely used, like I said, in the early 2000s. And then they were used for design, like how do I do things? Floodplain management, obviously, like with these floodplain maps that are done for FEMA. Also in dam break modeling. I did a lot of dam break models where you break a dam in the model, not in real life, and you see where the water goes. And so did a lot of that with these different models. And really, I used Flow 2D a lot with the two as a 2D model with a dam break. Um, and then the first major 2D model of the Reno Sparks area. And I mean, there may be some smaller 2D models done here and there for a different project or two, so I don't want to slight somebody. And I am aware that there was a Mike model done right after this for the Veterans Parkway that informed a 1D model. So there, but the first major 2D model of the Reno Sparks area was a Flow 2D model from approximately US 395 through Sparks down to Vista. And it was used in part to develop what we called the critical floodplain storage areas that local jurisdictions have in code right now. And this was developed in a 2010 to 2012 timeframe with some of the codes coming after that. So, that was a a big deal back then, but that model had issues. Now, for TURFMA, we really began using 2D and commissioning 2D models in 2018. That's when really it got started. And for us, it was going to be in HEC-RAS. In HEC-RAS, in 2014, they developed a beta of a 2D model. And I still remember the version number because I looked at that thing all the time as it was crashing on me. It was HEC-RAS 5.07 2D. So that particular model, and then the upgrades, the quick upgrades that were done that improved it tremendously over the last 5 to 7 years, made it more of a dominant model in the marketplace. I mean, a lot of these other models are really having trouble holding on because HEC-RAS is a free model with extensive documentation. So it's kind of taking over a lot of the design work as well as floodplain work, as well as dam break work. So anyway, so that we started using it extensively in 2018. So when I talk about 1D versus 2D, because this is a major innovation and it's going to play a very major role in how we actually design these projects going forward. Um, Both models use something called the Saint Venant equations, and that is a complicated set of. I'm sorry, I'll just say it real fast, and we can get on with this talk. Partial differential equations that are nonlinear. In other words, they're the worst things you can possibly imagine mathematically, and most of them are solved numerically because they're very hard to do in a closed form. So that's the Saint Venant equation. But there's different levels of it. There's a one-dimensional level where you're only doing it in one dimension, and that is what HEC-RAS up until 2014, 15 was doing. It was a one-dimensional model. Other models were one-dimensional as well. But then the two-dimensional models, it also works not just in one direction, up and down, but it works laterally, typically with these shallow water models. There is models that actually work in the second dimension vertically, but I don't want to get into that. That's overcomplicating things. But in shallow water situations like the Truckee River, these things work laterally. And the thing about a 1D model, it assumes you have what's called uniform flow. So as the flow goes upstream and downstream, there are changes to the bank, but they're not too bad. And so there isn't a lot of flow spreading out or lateral flow and things like that. If there's too much of that, the thing starts to fall apart. So a 2D model allows for that lateral flow. And it's a much stronger model. Like for instance, in the around 2010, 2011, I was running everything in Flow 2D instead of a 1D model simply because it was far more stable and worked a lot better because it just had better stability because I didn't have to worry about issue with uniform flow, which was a real problem with dam break floods when you have a wave of water going downstream in an unsteady manner. So anyways, so this is an example here of a two-dimensional model. This is an earlier version of what we call the physical map revision, Truckee Meadows model. And you can see here, when you get in the river here, look at how tight these are. Um, some of these are 7 by 7 feet, 10 by 10 feet. They're very tight, especially, and I think this even gotten tightened up in places more so than this. But the reason why is along these banks and stuff, it's very dynamic and you have to have it very tight. Out here where it's kind of flat and everything, you can have bigger grids. And this allows this particular modeling platform, the HEC-RAS platform, for instance, which is the one I'll be talking about, it allows for differential sizes of of grids, and some of the earlier models didn't. I'm thinking of River 2D that had at first they were all triangles and they were all the same size, and it was a very unstable model, for instance. So anyways, this seems to have a lot of capability as a fairly stable model, and this actually when we did this model, now let me just show something about a 2D versus a 1D model. This right here, I'm showing this. This is right from FEMA's website. See this BO, BP, and BQ? These are 3 cross sections over from Rock to McCarran. So this is an area where we own some property. It's about 110 acres. So I tend to focus here. It's got a lot of things going on with floodplain, buildings, flooding, floodway, everything. So anyways, with the old model, there were 3 cross sections in this area. With the new PMR model in this rendition here, how many grids are there? It's kind of like counting jelly beans in a giant jar. I mean, there's hundreds of them. You know, hey, Mitch, can you tell me how many grids there are right there? No, I'm just kidding. But anyways, there's a lot of grids in here, a lot more detail. Every grid, there is an input into the grid and an output to the grid. There's what's called it's an input output change inside the grid, and then it creates reactions with velocity, water surface elevation, etc. So, there's just tons and tons of calculations going on. And that's one reason why an earlier rendition of this kind of a model that was actually one-dimensional here, it had cross sections, a lot of them, and then it had these on the outside. That particular thing in the Reno Meadows area, which would, in this case, went from West Reno, it's actually a Reno model, goes from West Reno all the way to Vista, and that was done also by HDR. This is also being done by HDR. This particular model took, not this one, not the PMR, but the one that was for Vista Narrows, at one point was taking 72 hours to run. That it's just so much going on there. And if there's any instability in iteration, it gets really, really long. In this one here, somebody told me that they had it running in 9 hours the other day. So, I can run it on my computer in about 15, the current version of this. So pretty happy with that kind of speed, considering there are literally tens of thousands of grids here, if you look at the whole length of it. So 2D model development for TURFMA from 2018 to basically now. You can see there's 6 different major models that we've been involved with. Obviously, the old Vista Narrows 1D, 2D model, that was done for the Vista Narrows design. There was also a Vista Narrows area 2D model that was also done as part of that Vista Narrows initial design work by the Atkins team. HDR was a member of that, and they did that particular model. The PMR model, which was started in 2019, and we're still working on, and that has been actually turned into FEMA and gone back and forth. So it's pretty stable as a model at this point. But the idea is it was there was, it's a full 2D model, not a 1D, 2D. The North Truckee Drain is an associated model with it. It's a 1D, 2D. And then the Steamboat Area submodel that was also done is a 2D model. So this PMR model had a lot of components to it. There's also a downstream model as well that's a 1D model, but that goes all the way down to Wadsworth. Then we had the Booth Street Bridge 2D model that was done by Dyer, now called Jubb. Then we had the Rainbow Bend Long Valley Creek 2D model that was done by Dyer as part of the Atkins team. Of course, now they're Jubb, but that was part of that Vista Narrows design aftermath, trying to work on permitting issues and looking at impacts and working with downstream stakeholders. In this case, it was Story County. Then there's a Wadsworth area 2D model, Jubb at first with the Atkins team and then independent. So what I'm trying to say is we're doing a lot of 2D modeling, and it's for a reason. And it's going to help us a lot with our design going forward. So what does it do? How does it help, George? You just keep saying this, but what does it do? Well, you can better test approaches to solving a problem and get answers as to the best approaches. It's like you can experiment on something close to reality, and you have to understand the differences and the inaccuracies and all that, but you can test it and go, oh, okay, that works. Okay, that's a good idea. Ooh, that's not such a good idea. So it allows you to do that. Secondly, it allows you to be more aggressive. And this is very important with treatment. So if I'm doing a bank of a river and I have a 1D model or I have some ideas with some other calculation tool, and I really do not know what the velocities are along that bank, but I have some ideas. And I really don't know what the shear stress is, which is a stress that's proportional to the depth of the water and the velocity of the water. If I don't know that, I'm going to end up going conservative. So I may be putting riprap where I could have got away with some sort of bioengineering. That's just how it is. And with the 2D models where you can actually see the local shear stress and the local velocities, you can be more aggressive with treatments because you have more certainty about what the conditions are hydraulically at given flow rates. So that's why it's really important. And I'll show you an example of this in a minute. It allows you to better understand breakout behavior and understand things like how much water is breaking out, and if you contain it inside levees and flood walls, what will be the flow and hydraulic conditions inside the levees? And I will spell this out in an example here in a second for the Rock to McCarran Reach. It also allows you to test overall outcomes of treatments and determine issues such as local and overall changes in water surface elevation. And that's what we did for Vista Narrows. We wanted to see, if we build those Vista Narrow basically terraces and it opens it up a little bit, are we still backing up water into South Reno with all the loss of storage from all the areas we're drying out? We had to know that because we don't want to create a big problem in South Reno because we're solving a problem in Sparks and Reno industrial areas. So we want to make sure that we're balancing here. And we can do that with a model like this. We really, otherwise we're guessing if we don't have something like this. It also gives detailing as to wall levee heights and variation that may occur due to issues such as like the rivers coming around flow bin. You may have differential flow. It may be a foot higher on one side than the other. That's important to know that. You have to have a model that does lateral to really understand that. So in the 2D model does do lateral effects. There's other nuances. I don't want to really get into them, but whenever you have large roughness and things bouncing around, you need to understand what those effects might be. So here's an idea about testing approaches. And this was something that was done with JUB as our consultant. This is the Wadsworth, I'll call it the Wadsworth example. So here is a bridge, old bridge, and you think, well, there's not really much to it there, but there's also the abutments here and over here that are actually kind of in the conveyance path of the river, not kind of, they are, when the water's at 100-year flow. So the problem is our project, the Vista Narrows project, from another 2D model, was showing that we increase peak flows going downstream at Vista by about 2,400 CFS. Well, what would that do to this area right here, this area, in the area upstream? Because there is a mobile home park there, there is a canal, there's all kinds of infrastructure. Are we making it worse? Are we exacerbating the problem? Because it's already somewhat inundated. And we found that, yes, we were exacerbating the problem. So the next step would be, okay, so we got a problem. So let's do a 2D model of the area and, and find out what way could we do something to mitigate that problem. So the consultant JUB, looked at things like, okay, flood wall, levee, remove the bridge, raise the bridge, different alternatives. And how do you compare them? Well, you compare them by running them through the model to see if you're containing it, if it's a flood wall, see if it's attenuating it, lowering it, not backing up water, if it's a new bridge or a bridge removal. So you could test all those things. So after extensive modeling and iterative analysis, the consultant found that raising and extending the bridge would mitigate the effect of the increased flow at the site. And this option saved considerable money over doing a big flood wall or a levee or putting fill in and raising everything up. It also allows the residents to remain better connected to the river with better overall conditions in the river, because now the water isn't backing up and causing problems as much. So what does that look like? Well, this is, I showed you a picture of the bridge earlier. Here's a picture of the bridge like the day after or a day or two after the 1997 event. That's the top, that's the deck of the bridge right there. The stringer is in the water, and this isn't even the peak. So you could have things hanging up on that, backing up water, etc. I have another picture in here somewhere where you can see the mobile home park where mobile homes are inundated. And that's without our project. That's just the effect of the 1997 flood. So this is what this model looks like in terms of grids, by the way. This coloring scheme is depths. I extracted this out of the JUB model. This is what's called a profile line, because I want to see how much water is coming through this line under different conditions, like for the bridge and without the bridge and things like this. And that's what a model like this can do. You can test things. And obviously the consultant did a lot of this too, more than I did. They even had a cross section I think they had a bet among the office about how many feet down it would go or something. They were literally, most offices do like, the basketball thing with the 64, 68 teams. These guys are doing water levels. So you want to talk about nerdy. I bet you guys even did for Pi Day, you guys brought in a bunch of pies, right? Because at 3.314, that's Pi Day, 31416 was a big day for a lot of nerds because it was Pi Day. So anyways, nerd stuff. But anyways, we look at these things, look at the effect of this with project adding, I believe it's on the order of over 1,000 CFS into this area, more water coming through, more water going down that canal, more water into the trailer park, etc. So really a big effect there. And then this is from their actual report. When you make the bridge big or take out the bridge, you can see there's a big drop here under existing condition or under with the extra water from the the project, the 2400. And here with the bridge gone, look at that, it's less. The water surface is lower. Therefore, the amount of water going down that thing is lower. And the impacts on the trailer park and other things is slightly less. So we've mitigated the problem by doing something about this bridge. And that was a much cheaper option. It saved a lot of money. If we really had to, absolutely mitigate it, this is the cheapest way to go. And we discovered that through the modeling process, or the consultant did, or confirmed it at least. So that's an idea of how a model can be used that way. And I would expect whoever's doing, and I know the Atkins team did this on Vista. I know that whoever wins the Rock McCarran will do that with that project as well. So here's another thing to look at: effects on treatment choices. And this is something I worked on a long time ago. It's called the Napa Dry Bypass in the city of Napa. This is the dry bypass. See how the river is so meandering? The idea is to get the water through here to help with the flood levels here and even the backup here to some degree. So it actually helps bring the water levels down here and all along here and there as well. So there's a lot of questions to ask. Well, how high should this weir be? Like, how do I optimize this level coming down and all this? What kind of bed treatment should I be doing in this dry bypass when it's wet, when it comes over this thing and goes through it? What kind of bank treatment should I be doing along its banks? Especially down in here, there's an inner channel with banks. And then what about energy dissipation? Right here, we have a step dissipator with a downstream thing. But I need coefficients and variables to go into hand calculations of, hey, how much energy am I dissipating? How much energy do I have left? And things like that. So the model provided a 2D model from here to down in here, provides the split of flow, the breakout, if you will, of it going into this dry bypass. And it also gives me conditions of velocity, shear stress, things like that along here, where I, as a hydraulic engineer, would go, okay, it's okay to use reinforced turf here. Without the model, I would say riprap, or I'd say concrete. But because I had the knowledge of what the shear stresses were and things like that, I could literally say with confidence, no, a reinforced turf will work. And this was challenged in 2017. It was the worst case scenario, and it was a 10-year event, no backwatering. So it really had a lot of velocity through here. It held up just fine. And the reason why we knew it would, and we really weren't that nervous, was because we saw the velocities and shear stresses all along here because we had the model. Now, 20 years ago, I couldn't do this. There were some 2D models out there, but we didn't have the technology to do an analysis like this. And now we do. We have even better technology than I had in 2011 when I was doing this. I was doing this with something called RMA2, and I'll tell you what, we have a lot better technology now. So, this is back to this, reinforced turf versus riprap or concrete. The standing waves, how to deal with that. Well, I'm going to have some standing waves, so I have blocks to dissipate. Parameters for energy dissipation analysis. By knowing these hydraulic conditions, I could be more aggressive in how I have proposed treatments to make them more environmentally friendly. This thing is literally at an arc on purpose. I had it straight. Somebody goes, "Why are you doing that, you engineer? Make this thing an arc." And now it's called the Oxbow River Stage. They actually have concerts here. People sit on these dissipator steps and people set up in this grassy area, which is the reinforced turf that all the reinforcement now has kind of gone away from the sun, but now it's all set. So it's good. So anyways, that just shows you what you can do when you have the tools to be able to make those kind of calls. So moving forward with all these 2D models that we've been doing, how will that deal and how will that affect treatment questions along the Meadows Reach? Well, first of all, we have bank treatments to resist bank retreat or eroding banks or scour. We're going to need to know on the banks what's happening. Like, what is the shear stress? What is the velocities and things like that? And a detailed 2D model can give you that. Vegetative treatments and their effects on water height for given flows. Different types of vegetation have different roughness levels. And by being able to change that, you can look at that and kind of do an iterative analysis and try to get something that works right. Effects of extra water and how terracing would affect this. And I'll show this in a detail in a minute. It's basically, Danielle did a great job of talking about the environmental impacts of terracing and having floodplains low and things like that. But the other thing is when you have effective channel widening, you can norm some of the intensities of the flow being too concentrated, reduce velocities, reduce water heights on the sides, etc. And you can look at that and see what the impacts are and what the trade-offs are for going wider or narrower. Erosion resistance and treatment for any of the planned side channels or planned breakouts. So if you have something where, like here, I'm thinking about having a sacrifice area or a wettable area here that can fill up at a strategic time, okay? If we have the 2D model, we can understand what the shears and everything are over the top of this, what the velocities are, and what kind of treatments we have to do as this filling up so it doesn't create a big eroded mess. And then detailed determination of wall and levee height. So as you go along here and the river's curving, what does that do to levee heights sometimes? Sometimes it may influence that. And so you have to know these kind of things to be able to have a consistent protection level. Sometimes people will design a wall and they think they've got it right, and effectively in one spot it's much effectively lower than the other spot because they didn't take account of all the different things that can make the water bank up in that spot. And these are some of the things a 2D model can get at because it tracks lateral flow. Okay, here's an example. We have the colony's levee and flood wall height. This is already built. Back in the day, it was determined with the best available information. It was built with considerable freeboard to the 1997 flood level. So basically, they took the 1997 flood and added 3 feet to it. And that's locally right there where the 97 flood hit, plus 3 feet of freeboard. Now, if I start building more levee and flood wall, or more levee, or berm, or whatever I'm building, I want to be able to match the capacity with no breakout to the rest of the project. So I don't want this to be over-designed or under-designed. I want it to all kind of be balanced. So with a large-scale 2D model, I can know at what CFS this thing's going to overtop. And if I know that CFS at that spot, that would correspond to X CFS maximum down at another spot, like at Rock McCarran or at the airport or whatever. And so I can balance my heights. Now, before, there was a lot of guesswork in doing that. With a 2D model, there's much, much, much less guesswork. So that's an example of this. So as you go down the river and you look at the different things that we're going to look at, I mean, this is the GSR. They're talking about $1 billion expansion here. They're going to do a lot of things, but they want to work with us and we want to work with them to make sure that they're protected from flooding. And a lot of this is we want to build up a berm here, a levee here, and another berm area here. Well, how high does that berm need to be? Well, we need to know that. what kind of treatments do we have as this water level comes up? What is this water doing? Is it very fast? Is it scouring? Is it just slow back in this area? Is it okay? You know, what kind of treatments do I have to put on this berm? What kind of treatments do I have to put on this levee? I've got a bit of a bend here. This might be a challenging area. And the 2D model is going to give me some ideas about that. So as I look at these treatments and I'm trying to be innovative and backed off as much as possible and using bioengineering and native treatments as much as possible, I have the tools to be able to go as far as I can go. Over here, I have an offset levee. So that what's the effect of the offset? If I offset a little bit more, is it a big effect or a little effect? How high do I need to be since I'm offsetting? The original design was a wall and a wall right against the river. Now I back this off. Can I go a little bit lower than what they were talking about with the wall? Yes, I can, but how much is it? See, so there's just a lot of questions that the 2D model helps answer in a place like this. The airport reach, when you look at the airport reach, here you come, there's the Sparks, there's a Sparks Park here, the Rock Park, and then there's this water feature here. So you got to understand what's going on with this water feature and how it's affecting the berm height that's going to be needed there. You're going to have to like if we do some terracing, how far should we terrace? Is there a kind of a optimal point, or is there, is terracing kind of not that big of a deal? We need to know that. What kind of vegetation? What will the vegetation do to the water height? There's a possibility of a need of a small levee over here. Well, how small? How high? Well, we need a model to do that. When we put this in, what does it do to this? So these are 20 years ago, like I said, I'd be guessing. I would be doing a 1D model and I'd have cross sections like every, a quarter mile or something, and I'd be guessing in between. Now I'm not guessing as much. So now you get to Mill McCarran or Rock McCarran. So you look at this, okay, so I'm going, okay, how wide do I want these terraces to be? And what do I gain by having it wider? And I'm going to show you a slide about this in a minute that's kind of mind-boggling. So, how wide should this be? What will this do to velocities? What will this do to water levels and things like that? How would that affect these levee heights? I need to know it from the 2D model. Here's this, what I call an intermediate levee. How high does that need to be? And if I put a low spot here and let it fill up, what should that low spot height be? What's the optimal height to take the most off a 100-year peak flow, assuming a certain type of hydrograph? We can know that now. Couldn't know that before. Once again, how should I configure this channel? What's sustainable? What dimensions of channel are stable? Things of that nature. All of these things you can start to answer with that, and you can start to use these tools in an optimal way. So yeah, I put in a detention basin. If I put in the wrong height, it's a joke, right? It's not going to help me. If I don't do these terraces at the right height, I could screw everything up and have a whole bunch of erosion. So when I'm using all these tools, I need some advanced ways of checking to see what I'm doing will work right. So now this is an attempt, and I did a small contract with HDR to add to the PMR model the elements of say Rock McCarran, the airport, GSR, Tumwa setback levee, etc., and the north levee flood wall along Sparks that protects the industrial area. So they put all that in. So now what do we have? Well, we have a regraded terrace. We have an overflow. This isn't the final design or anything, but it's kind of a guess. They put some sinuosity in there. They were in a mood, so they put some sinuosity in. So you had all this going on. And so the next thing you do, well, here's the model. Here's the grids. You can see how tight this is. Now the detailing in this area is pretty tight. Then you run the water through. So this is near peak type of a thing. You've got water coming in to this sacrifice area. It's attenuating the peak that's coming off this bridge somewhat, and it really needs to be attenuated some because a whole lot of water is going through this bridge right now because all this is now dried out. Sparks is dried out. Reno industrial area is dried out. The airport's dried out. What does that do to the flow that's going through here with all that dried out? Well, we know now with the model, because we know what the breakouts did do, and now we know that without the breakouts, this is what you get. So instead of running about 12,000 CFS through that reach, the Mill-McCarran reach, on the same peak flow event, you'll run 20,000 CFS. So to go back to this, it's going to be really important to know how wide you go and what this does to velocities if you're running 20,000 versus 12,000. It's going to create quite a stress here. And whatever you do with the channel and with the floodplains, the treatments have to be robust and sustainable. Maybe we have to pull this out further, and we just don't have room for this sacrifice area because we're trying to spread this out more to normalize these hydraulics a little bit. See, there's a lot of questions you can work with and answer when you have a 2D model. Without it, you're guessing and you're hoping you go okay. But here you have a lot more information to make a much better determination. So going along here, this is the north levee. And there's questions here. What are the heights? Where are the weak spots? Maybe we want to break this up and do it in chunks, as we get funding. So where do you go first? Where's the real bad spots? A lot of that will be determined looking at a profile line along here with the two-dimensional model. So you really know where your problem areas are at, along with walking the reach and everything else. So another case for this. Then you get to, this is another look at it during the 2017 flood, which was not a very big flood. It was about I think it was on the order of about 12,000 or so CFS off the top of my head. So then you got Vista Narrows, which is the lowest project of the big projects, and everything below is those restoration projects. So we originally had 6 terraces that were being looked at. It was narrowed down by HDR to 3 terraces. And what we were trying to do is balance the meadows benefit of having, no backing up water in the South Reno, having a no rise condition with downstream impacts. We only wanted to do enough so that we didn't have a negative impact there. We're minimizing the downstream impact that way. And so you had to know how many terraces, what levels, and how big, and what kind of vegetative treatments that cause what kind of roughness. You put all that into a model, and I believe this was a local 2D model that was used, and it was a full 2D model to figure out the treatments, what kind of velocities you had, and they had that all laid out because they had all this information. So HDR was giving that to the Atkins designers. The designers had all this in front of them because of those models. So what does this look like? It looks a lot like the downstream restoration projects, for instance. And so will Rock-McCarran for that matter, because there will be terraces and there will be plantings and there will be added wetlands. Danielle can correct me, but I think it's somewhere around 18 acres of wetlands. And then there's also added riparian habitat, etc. So there's added habitat here in the floodplain, and all the good impacts are there. If you look over, I'll do it on the next slide. There's a much better slide for this. So on the next slide here, you can see this is kind of exaggerated, but these banks are terrible. This 15-foot high bank at Vista Narrows. There are some areas along the University Reach across from that North Bank levee that are worse than this. They're 20 feet and just terrible eroding banks of material. So here, what we're going to do is cut these back. That's a lot of material. That's just one little cross section that goes on for hundreds of feet. So a lot of material gets taken out of here, and you reconnect this floodplain with the river. The river was lowered when somebody decided to take out a outcrop of a rock at the Vista. So the river lowered down. And so now this is disconnected. That's white top right there, an invasive species. We want to get this down. We want to have cottonwoods, willow, better habitat, better shading, more complexity during high flows. So fish have places to hide when the velocity gets high. Other aquatic organisms have places to hide. There will be wildlife habitat here. That's the idea behind this, is we do this. So a final thing is a model helps you understand the overall outcome of a design. So this is an old rendition from 2014, and it's not trying to be exact. It's just trying to give you the broad areas that would come out of being inundated, and give you an idea. Wow, all this industrial area. Wow, big chunks of the airport, the Reno industrial area, GCR, or GSR. All these things come out of being inundated, and it's a massive economic benefit. Okay, but that's good, but that's kind of general. It's broad areas. There's like no, obviously the island over here is not underwater, for instance. So now let's do it with the 2D model in more detail. This was just done the other day by Mitch Blum from HDR. You can see here, it's more, you're looking at a scalpel here. You're understanding exactly what's coming out of inundation. Some of these buildings are surrounded. It's able to get into the floorboards, others it isn't. So you have to kind of work through this detail by detail, but you got a much more detailed, precise look at what the actual benefit is, which is the area in red goes dry, and it was inundated before. The area in blue is remaining in water. And the idea here is we do not want this area in blue right here to be higher than what it was. So we don't want these homes being more affected than they were before. We want a no rise condition, either a little bit lower or the same. So these are things that we're testing. We can test this with the two-dimensional model. And the cool thing about this model is it's highly detailed, based on LiDAR, and it's calibrated. A lot of models are not calibrated, and typically hydraulic models are a lot more precise than a hydrology model, and a hydrology model is a lot more precise than a meteorological model. But when you calibrate a hydraulic model, it becomes even more precise. And I'm not saying it's not calibrated to every spot, but there are numerous spots where this is calibrated to try to get it to be more accurate. Okay, this is just the lowering of the water level. With just Vista Narrows, it's much lower. You can see a foot lower, but when you put the whole project in, it's just perhaps just 0.25 to 0.1, like an inch lower. We're just trying to get that no rise condition. You can see now the island showing because we're getting more exact. Okay, so the downstream effects were 2,400 CFS. And this was using what we called our locally preferred plan in that configuration with what we called the Vista model. So what we wanted to understand is when we use the Meadows configuration, which is different, it's more backed off, there's more terracing, things like that. When we do that, what does that do to this? And when we use a more accurate model that's calibrated, what does that do to this? So when we do all that, what we find out is we get this. This is at Vista, at the Vista gauge area. And you can see the difference here between this and this is slightly less than 2,000 CFS. It was 2,400. CFS. So it's actually a little bit better, which is what I would have expected, because of the backing off and a little bit more opportunities for attenuation. So to kind of summarize all this, the features and strategies that are kind of new, some are a little old, but they're really coming online only in the last 10 to 15 years and really heavily used only for the last 5 or 6 years, is the use of a 2D modeling to be able to analyze treatments and effects. That's one thing. A second thing is the terracing and setbacks to optimize velocities and treatments, as well as flow conveyance at Vista and at Rock McCarran, and possibly even the airport reach. This also includes the benefits of floodplain restoration that Danielle talked about, but we're really trying to optimize, get the level right, get the vegetation and the roughness right, so you optimize what these things are doing. Thirdly, a strategic detention at Rock and McCarran to attenuate flow, getting when that water comes in, at what height it comes in, for how long it comes in, to really take as much water as you can off that peak that's hitting that bridge. That's helpful. Finally, channel configuration to optimize attenuation and restoration opportunities, especially at the Rock McCarran reach, where we might be moving the channel around, and also making sure that that channel, when it is designed, is something that's sustainable. You don't have a missized, misaligned channel that will just fall apart. You have to be very careful with that. Okay, so I'm done. Are there any questions about any of all this? I went through this real quick, but I wanted to really stress that there are things that are different. So if you were around in 2008, 2009, you had a lot of the same ideas, but how do you implement them effectively? Now we're starting to have the tools to be able to do that. Okay, questions, if any? No questions? If you have a question, just come unmuted and just ask. Okay, I'm going to turn this off so that I can see everybody, or see if there's any questions. And we will stop the share. And do we see anybody? Okay, I guess.
Yes, this is Susan Lynn.
Okay, thank you.
Back on your slide that was the 2D versus 1D, there was light gray and dark gray and two different colors of green. You return to that slide and tell me what the depths might be.
Okay, let me,
it's past, but it'd be nice to know what.
Okay, let me see if I can find that for you.
It was fairly early on.
Okay, let me share this and then go back a bit. Okay, let me get into this. I think I know what you're talking about. This one?
No.
Okay.
It was early on and it was called 2D versus 1D.
This one?
Yes, that one.
Okay.
So in this diagram, there's the very light gray and the very dark gray, and then the very, very dark gray. And then you have different levels of green. Does that mean that the white and the gray are going to be out of the floodplain, or is this just an example?
They are dry. And this is not the final floodplain determination. This is what a model is showing the extent of inundation. So anything in green is wet. It could be like even 6 inches wet, you know. And let me just show you a couple more slides. This is the same diagram but bigger.
Yes.
To show the comparison with a 1D model. So you can see this area is out.
Yes.
And one of the cool things that I can do, and I do this a lot for people that live in the in the area down by Hidden Valley, in that area, is I can actually find your house on the model and go, okay, here's where the water is, and I can point the pointer in the model. I don't, I'm on a PowerPoint right now, but I can actually stick that thing right there and have it set to tell me what the elevation is. And so then I can compare that with your home elevation and tell you what's going on there at that spot, which is really helpful for some people that really want to understand what their risks are, with their home or something like that.
Oh, right, and I understand that, but it
Yeah.
looks like there's still some risk along the streets, using them as kind of canals and,
Yeah, they're typically lower and they typically convey water.
okay,
And like especially things like this is I believe this is one of the side streets and it kind of just gets in there. Same thing happens on Edison right here, for instance. It goes down and
I
gets
was looking on the north side, which I think is Coney
okay.
Island or,
Yep, yeah, that's the Coney Island area, and there's that too. But yeah, the streets are often wetter. The properties tend to sit up off the streets a little bit.
yes, they
Yeah.
do. Okay, so is this going to be lower as a result of the project between Rock and McCarran, or is it going this kind of the end result?
Let me show you what it'll be.
Okay,
This is
thank you.
I have an actual slide of this to give you an idea. I mean, I'm sorry about this slide. It's not very translucent, so you can't see it very
You're
well.
doing very
It's
well.
really, the red is red, you don't get to see through it. But
Okay,
anything in red is going to be dried out. So this
okay,
was previously all wet, like all
yes,
this. Now it'll be gone.
okay,
Anything in
okay.
red is, the airport had water on the runway.
It
Yeah,
certainly
there's
did.
that famous picture of the jet, half with water all the halfway up towards the door of
Yep,
the jet and all that. That will dry out. That
okay,
all dries out. Um, whatever's in red goes away,
okay, okay. Thank you.
Yeah. Let me go ahead and pull out of this again. It's not hard to go back in it if I need to. Anybody else have a question?
George,
Yes.
this is Rose Strickland asking
Hi,
a
Rose.
question. I just participated in a river cleanup below the sewage treatment plant. And that area was occupied by homeless camps. The area north of that, on the other side of the river, are homeless camps. The area is the vegetation is beaten down by the wild horses coming over from the Virginia Range in Story County. And I'm looking at these wonderful pictures of terracing and greenways and floodplain restoration. And I'm thinking, boy, that would make a really nice place for more homeless camps. Have you guys started thinking about how to deal with the unintended impacts of what may reduce your chances of successful floodplain connections?
Yeah, I mean, in the when you talk about like the detailing of the plan for Vista Narrows, because it's about 65% done. And all they have to do is get to final. So there's a lot of information, a lot of discussion about how to deal with different things, such as how do we maintain vegetation? And there is a problem with the horses coming in there, like you just said, because that area is part of Vista Narrows, that part of the Vista Narrows project.
Right.
And so there are things about the horses. I am not sure we had a lot of information about how to deal with homeless people. We have that problem at Rock McCarran now.
Yes,
and it beats up our riparian areas, and we try to control it. We try to have, you know, whenever we can, we try to get the police out there. We try to have other people that help intervene and help the people, such as Karma Box and Rise. So we're doing everything we can, but it's a very big societal problem that you know, we're just kind of a, I hate to say it like this, we're kind of a victim of it, and we're not really the player to solve it. But we're, you know, we're looking at the camping ordinances and hoping that if they're enforced correctly, that will help cut that down in that area. Washoe just passed one of those. So you know, I'm hopeful that will cut down that area somewhat. And we just try to stay on top of our property at Rock McCarran as well. That's 110 acres. There's a lot of places to hide there. So it's an interesting issue that I didn't know I was getting into when I took this job. But it's been
I'm not,
very interesting.
well, I'm not sure a model could possibly deal with these kind of social and cultural issues. You may have to expand your plans to deal with these kinds of issues.
Yeah,
Because
and we do that. Where we deal with that is the detailing and the operation and maintenance. Because that's an ongoing, that would be an ongoing issue, like with the horses.
right,
How to get the horses to water so they don't, you know, die of thirst out there in the dry period of the year. On the other hand, do it in such a way that they don't like trample the whole area. You know, these are hard issues that is more like implementation and O&M. Danielle, would you like to speak to any of this? I think I'm capturing what I've been told on this quite a bit.
Yeah, I mean, I don't have a plan for dealing with homeless encampments. I know that George and myself are involved with a lot of other agencies and entities, and, you know, the cities and the county who have jurisdiction over enforcement of their laws and ordinances. You know, there's a lot of regional effort that's going into trying to address this problem. So we're part of those conversations, and we'll try to incorporate what we glean from those meetings and our partnerships. In terms of the wild horses, we do have some plans for fencing in the Vista Narrows project area. And some of that is temporary, I believe, to protect the vegetation while it's being established. But we have had feedback from wild horse advocates, and so we will ensure that the horses do have access to water in that area. I hope that helps.
thank you.
Mhm.
Hey, any other questions? All right, well, thanks for coming, everyone. And yeah, see, it went down as soon as you were done. It was like 22 and it went down to 16. Anyways, thank you for coming. And we plan to have more of these on certain topics as time goes on. Some of these we've had upwards of 50 people showing up. So I'm really excited to convey information so that you're more informed about what we're up to. And I hope this helped with that, to give you an idea of some of the tools we're using, strategies we're using. Looks like we got some chats. Maybe I should check those. Oh, 13 acres. Thanks, Danielle. I said 18.
Yeah, sure.
All right.
Mitch
Uh,
was telling you the amount of cells.
Yeah. Whoa, look at this. Marty gave me the shallow water equations.
That was for everybody else. I think you know them.
Ooh, she did it on Wikipedia, but you know, that's pretty, Yeah, shallow water equations. Okay.
All right, thank you.
Anyways, I don't know a lot of people that actually run HEC-RAS that actually know that stuff, but some of them do. Anyways, all right. Thank you. And have a great day.
Bye.
All right, bye.
Thank you.
Thanks, everyone.